Hey everyone, welcome back to the another video of Engineers Academy. And guys, in this video we are going to talk about the Avogadro's number, which is basically used to calculate the total number of atoms, total number of molecules, total number of ions which is present in the matter, which is present in the substance or an object basically. So guys, welcome back to the another video of Engineers Academy. Myself Narendra, and you're watching the playlist of thermodynamics. So basically over here in this playlist we will be covering different laws, different kinds of working of different equipments, different laws, different cycles, different mathematical formulas, expression, derivations. So guys, please watch my video till the end, and guys please do subscribe to my educational channel Engineers Academy. So guys, basically your subscription, your like, your comment, that really motivates me to make more of this educational videos. So guys, without wasting any time, let's begin with today's topic, that is of your Avogadro's number. So let me give an example. Suppose I'm having a container which is filled with marbles. Totally, like the marbles are filled in that container. So right now I'm asking you, what will be the total number of marbles in that container? So guys, most of you will say that is very easy question, and the total mass of your container which is filled with marble divided by the individual mass of that particular marbles. So that will give you the number of marbles which is there inside that container. So guys, that's totally correct, and that's very easy also. Suppose I'm having the same container which is filled with water, and now you guys tell me what is the number of this H2O molecules which are there present in that particular container. Can you please give me the answer of this? Can you please comment down the total? 150. I'm having a container, I'm having a beaker which is filled with 150 ml of water, and can you please comment me this the total number of H2O molecules which is there inside that particular beaker. So guys, over here interesting fact is that in the atmosphere most of the gases like helium gas exists at the atomic stage. Hydrogen gas exists H2 at a molecular, like the two atoms forms one molecule. H2 will be there at a molecular level, and like NaCl, salts exist over there at the compound level. This is basically compound. So this exists in a combination, that is the molecule of NaCl, one molecule of NaCl, that is exists in a compound stage basically. So guys, over here in this case we have to count the number of H2 molecule, number of helium molecule, and number of NaCl particles. So this is nothing but the counting methods. We are counting as per this type, that is the atomic level, molecular level, and at the compound level. So guys, basically over here we are dealing with these counting methods. So in physics, suppose I'm having a one pair of shoes, that is nothing but the two number of shoes. I'm having 1 dozen of X, 12 number of X. I'm having one ream of paper. It means one ream is equals to 500 sheets of paper. It means I'm having a total number of sheets, that is 500. Now let's talk about I'm having 1 mole of water. So mole is another counting method which is there used in your chemistry, which is used in the thermodynamics also. So guys, over here this 1 mole of water represents your 6.02 into 10 raised to 23 number of this H2O molecules. So over here the mole is very much important, and this mole gives you the number of atoms, number of molecules, number of compounds, that is number of NaCl molecules in case of NaCl, salt, number of H2O molecules in case of water. So guys, over here this mole gives you the number of representative particles. So guys, why over here this 6.02 into 10 raised to 23? So guys, over here this 6.02 into 10 raised to 23 is considered as the Avogadro's number. So we have to remember that this particular number 6.02 into 10 raised to 23 is nothing but your Avogadro's number. So basically, Avogadro, he was a scientist, and basically in the honor of that scientist, that particular number is like basically this is used as a standard in chemistry and thermodynamics. So basically, why this 6.02? So this 6.02 represents your molar mass of your carbon atoms, that is the 12 grams of carbon. So it is the 1 molar mass of 12 grams of this carbon atom is nothing but the 6.02 into 10 raised to 23. So guys, over here, that is the reason, and from the ancient times the carbon is used as a reference in chemistry. So this is the main reason, this particular, like the molar mass of carbon, which is used as a reference standard, and it is termed as the Avogadro's number, that is the 6.02 into 10 raised to 23. So guys, let's go back to our first example. That is, in a container I am having 150 milliliter of water, 150 ml of water. What will be the number of representative particles over here in that particular beaker? So over here the representative particles are H2O molecules. So over here we need to find out the number of H2O molecules. So the total volume, volume is there, that is 150 ml. Now that convert that 150 ml into grams, that is 150 grams. So now let's talk about the molar mass of particular water. So molar mass contains the in each of the gram, how many moles are there? Milliliter, liter, grams. So in each of the grams, this is the counting method. If we go in deep, like grams and then moles, what will be the the total number of moles in per gram? So that's why in case of water, okay, we need to count the molar mass of this particular water. As this particular water contains of hydrogen and oxygen, we need to calculate the molar masses for this hydrogen and oxygen. So the atomic mass of your oxygen is 15.99, whereas in case of hydrogen, that is 1. So that's why 2 units of hydrogen, that is 2, and 15.99, that is the single unit. So combining all this, adding all this, we'll get the total grams per mole, that is the 18 grams we get per mole. It means there are the 18 grams of this H2O molecules are there in 1 mole. So that is nothing but your the molar mass of water. So the 18 is the molar mass of water. So total the total weight of your water is 150 ml, 150 gram. So 150 divided by your total molar mass of your particular water, that is equals to 150 divided by 18 into your Avogadro's numbers. So over here, that is equals to 150 divided by 18 into 6.02 into 10 raised to 23. So guys, over here this will give you the total number of your H2O molecules which are there in water. So guys, after solving this particular equation, we'll get a value of 5.01 into 10 raised to 24. So that will be your total number of water molecules which is present in 150 ml of water. So guys, that was the example of this particular compound, and in that particular example we use this particular term as molar mass. So guys, over here in case of gases, what will be the conversion factors, what will be the total weight of that particular gas to your into the moles, basically, that is the grams per mole of gas. So that is not possible over here. Over here we will be talking about this particular liters. So over here these gases will be having a certain volume which is there in liters. Suppose, let's take another example. I'm having a neon sign which is filled with your neon gas, Now the volume of the neon is this 200 ml. So over here this 200 ml is nothing but the 0.2 liters. So over here, in case of this gases, the gases are for this particular gases, if we convert the volume of the gas to the number of moles of the gas, so that's why you need to maintain the STP over here. So STP is nothing but the standard temperature and pressure. So over here the standard temperature is 0 degrees Celsius and the standard pressure is your 100 kilopascal. So guys, you have to understand that over here in case of gas, the total 1 moles of the gas is equals to 22.4 liters of your gas. So 1 mole of gas contains 22.4 liters of your gas. So that is that is the reference standard in case of gases. In case of liquids, we have used the term that is the molar mass, and over here we will be using the this particular 22.4 liters of your gas. So guys, in this example of neon sign, I am having this total volume of neon, it is 200 ml, that is 0.2 liters. So right now I need to find out the total number of neon atoms which is present in that particular signboard. 1 mole of this neon will contain this 22.4 liters of neon gas, basically 200 that is the 0.2 liters. 0.2 divided by 22.4 into 6.02 into 10 raised to 23, that is the Avogadro's number. So this will give you the total number of atoms which is present in that particular signboard. So this will give you the value of 5.375 into 10 raised to 21. So this is the total number of neon atoms which are present in that particular signboard and having the volume of 0.2 liters. So guys, over here in this video we have seen this particular moles. It is related to the solids in terms of their masses, liquids in terms of their masses, and like in case of gases it is of 22.4 liters. So that is assuming the standard, assuming the STP over here, standard pressure and temperature in case of gases, to find out the total number of atoms in case of gases. So guys, this mole plays a very key role while calculating the total number of atoms, total number of representative particles, total number of molecules in case of your different objects, different substances. So guys, this is the 6.02 into 10 raised to 23 is considered as this Avogadro's number. So guys, over here in this video we have seen the Avogadro's number, the conversion factors, we have seen the molar mass, we have seen the STP for gases. So STP for gases. So guys, I hope you understood this Avogadro's number. So guys, thank you for watching my video. If I miss anything, just please comment below, and guys, please do subscribe to my educational channel Engineers Academy. Guys, thank you for watching this video, guys.